We are happy to do all the calculations using finite element method. It's very easy to use and so on, but we need to be really concerned about how much error is there in the computation. And that is very, very critical. So like other sections though, here is a quick introduction to how we estimate and reduce error in finite element method. It is intended for an undergraduate course in modeling and more in terms of the applications. So here we do not get into any formal aspect of error analysis. Nevertheless, we need to have some idea of what error is and how much error we could be making and how do we reduce that. So that's what this chapter is about. So we'll talk about defining, estimating, reducing error, and then how to accept the overall model. So first, we just want to define error. Now, in a separate video, we have discussed all the different types of errors that we can make in computation, starting from just simply usage error or computer programming error, convergence error, or round off error, and then discretization error and reality approximation error, or how much error we make by approximating in the physical process into a governing equation and boundary condition. Now, the two that are most significant are these two. Okay, and of these two, the one that is in the context of a specific numerical method is the discretization error. So that's what we are really after right now. And it is the error that we make when you approximate the true solution of a differential equation with the approximate solution to the algebraic equations that we get using finite element method. So this one is one of the two major sources of error, and that's what we're going to talk about. So how do we define error? For that, we go back to the finite element method. And what we discussed there is if we have a true solution, okay, and then we develop our finite element solution, which for a two-noded element, we're going to get two nodal temperatures. Okay, this is the other temperature, and any point in between would be interpolation between those two temperatures. So this one is my computed solution, and this one is my true solution. So error is defined as the difference between the true solution and the finite element approximation. So what I am hatching here are the errors. So it's the difference between the two. Okay, and so over the entire domain, we can calculate a single function. So we can calculate error at any location and square it. So error is the difference. We square that and integrate. Integrate means we're adding all the errors, so the positive and negative errors don't cancel. We have that's why we need to square it. And so now, and we take the square root, so it comes back to the same dimension. If it is temperature, it comes back to error in temperature, and so this is my error over this entire element. Over this entire element, this is the measure, and we can do this over all the elements. Now it's very nice to have defined this, but we have a big problem. We have a big problem. And the problem simply is, do we know this guy, true solution? Do we know this? If we did, we don't have to bother with the finite element method. We already know the true solution. So we don't need to do this method. So obviously we do not know. So this makes a huge difference in terms of the error calculation. We do not have the true solution. And so now we have to do something to get around this. I want you to see this. So how do we get around not having the true solution? We are going to try to estimate the error, because we cannot get the exact error because we don't have the true solution. So we do not have the true solution, and we still need to get an estimate of the error. So how about comparing with a solution that is somewhat improved? It turns out that's all we can do. So the question is, how do we get a somewhat improved solution? So here are two of the common ways to get somewhat improved solution. First is the difference between discrete values that we get from doing finite element solution and a continuous approximation somehow created. So we'll see how we can create it. So we get a discrete value, and we kind of say that the solution, the real solution, cannot be discrete. So if we can get a continuous approximation, that must be somewhat improved. The other one, which is the most common way of getting this somewhat improved solution, is the difference. So we get the error as the difference between the solution we got and another discrete approximation. So yet another discrete approximation. So we do not have the true solution, but it's another discrete approximation, but one that is slightly better. So one that is slightly better. So we're going to do two of these. So we'll try the first one, the first approach of getting an error estimation, which is to compare the discrete solution that we get by solving the finite element equation with some sort of a continuous approximation that is supposedly maybe little improved. Okay, so let's see how we get the continuous approximation. So we're going to talk about this problem, which is heat conduction in a slab, 1D slab. And so the governing equation is del T equal to alpha del square T del x square, where this is my x, okay, and the domain is from here to here, and I'm going to divide it into 6 nodes, okay, and so that means 5 elements. So it's 2-noded 1D linear elements, and I do the computation using finite element equations, and this is the solution that we're going to get. For temperature, the solution should look something like this. So the solution looks, you calculate the nodal values, and then in between you join using a line, right? And so from these temperatures I can calculate flux. So how is heat flux defined? heat flux is defined this way, so it needs the gradient of temperature or the slope. Okay, so since the slope is constant because of this linear element, within an element the slope is constant, right? But it varies from one element to the next. So then if the slope is constant, then the heat flux within an element would be a constant. So let's plot that and let's see how it looks. So then within an element it is a constant value, but in a different element, let's say this one, it'll be different. Okay, because the slope is different, obviously. Now, is there any reason for flux values to jump around like this? So at some point it jumps. Is there any reason? This equation certainly doesn't talk about this kind of jumps. And physically, why would temperature at any or the flux at any location be different on this side versus this side? There is no physical reason and there's no mathematical reason for this kind of discontinuity. So then what we can do is, because this is physically impossible, the flux should really be varying continuously. And so what we can do is get some sort of a continuous approximation. So we could simply do this. We could take the midpoint of these fluxes and join it by a smooth line. Okay, so fit a curve through this. Okay, so we say that at least this curve is more realistic for this equation. It makes more sense that the solution is a continuous quantity. So we have no idea whether this guy is the true solution. In fact, it's probably not, but it is likely to be an improved solution. And so we use this improved solution as a proxy to the true solution and define error this way. So this is my improved solution, and this was the one calculated from finite element. So my error is the difference between these two. So this is my error, and here is error, and so these are all errors now. So that is how we're going to define the error. It is simply simply the difference between what I calculated, which is discontinuous because we calculated over the elements, and compare that with a continuous flux that we just created from the previous solution. We got this continuous flux from the solution, and then we're saying, well, this guy is likely to be closer to the true solution, and we're taking the difference between this guy and the discontinuous flux that we computed from the finite element. Now we try the second approach to try to estimate an error. So the second approach is the difference between a discrete approximation that we get from finite element and another discrete approximation that is slightly better. Okay, so how do we get another discrete approximation that is slightly better. Recall that when we solved the heat equation using finite element, we showed that if we had a two-noded element, computation of that versus the same size element but a three-noded element, the second one was better. It performed better. So the three-noded, because it had the extra node to interpolate, and it can give a quadratic fit, it gave us better solution. This is the idea we're going to exploit. So computations are repeated for one order higher shape functions. So if you had a two-noded element, then we repeat the computation with a three-noded element. Likewise, if you had a three-noded element, we can repeat that with a four-noded element. Okay, four-noded element. So compared to this one is better. That sounds like a lot of computation, but computers can take care of that. In one software, COMSOL, this is set up accordingly. So you provide two quantities. One is an absolute error and the other is a relative error. And they are used this way. Suppose we're calculating temperatures and the typical temperatures in the computation are around 300. Then the values that you provide are used this way. This 300 is multiplied by the relative error that you provide and added to the absolute error. So in this case, since you provided 0.001 in both cases, and then they don't have to be the same, of course, they can be very different. So by plugging in the numbers that you provided with the typical temperature values, what you are saying by providing these numbers is you are telling that E, or the error that I'm going to allow, is less than 0.301, which is 300 multiplied by this quantity added to 0.001. That gives me 0.301. So again, you are saying that the error in my computation needs to be 0.301. That's what effectively you are saying when you are providing these two numbers. This error E is the difference between two computations. So if you did a two-noded element computation, then you repeat it for a three-noded element, and the difference between those is what we are calling as error. Likewise, between a three-noded and a four-noded element. Symbolically, if we are calling the absolute error as A and relative error as R, so what we are saying is E should be less than A plus R times T, where T is my solution variable, or the temperature, in this case the temperature, solution variable magnitude. Okay, so we're saying E should be less than A plus RT. So in other words, check if E over a plus RT is less than 1, because E should be less than a plus RT. So back to the numbers that we had plugged in. So in this example here, we are saying E should be less than 0.301. So after you do the calculation, if E is more than 0.301, then you reduce the time step and repeat the computations. So when you reduce the time step for a smaller time step, it's going to make less error. And so we would repeat the time step, and hopefully next time it'll go below that. Otherwise, we keep repeating. So again, symbolically, then we want this to be true, E over, and so what we do is we do this over the entire domain. So we do this over the entire domain, adding up over all the nodes. We take square of this quantity, we take the square of this quantity, and then add them up, divided by 1 over n, and take the square root, and that we want it to be less than 1. If that is not satisfied, meaning after calculation for one time step, if this is not true, the error calculated does not satisfy this, then the time step is reduced and the computations are repeated. Okay? And so the values of A and R are provided through these windows. So I'm showing you the first one. So in the study, if we go to time dependent, if we click there, then we have access to this relative tolerance. So we can provide the value of relative tolerance here. After that, then you click on this time dependent solver, this one, to get this window where you input the absolute tolerance. Okay, so once you have put in absolute and relative tolerance, it can check whether error is less than the absolute plus relative tolerance, not exactly using this expression, but the one I showed earlier. So it checks that, and once it knows that this is satisfied, it can keep making progress. And how it uses it is it tries to take larger and larger time steps while keeping the error still less than this value. So when the solution is not changing as rapidly later on, it can take larger time step and the error would still be less than this. And this is an example of how the computation looks like. So what's plotted here is 1 over delta t. Delta t is the time step taken, and delta t is the time step taken, so 1 over delta t. So initially, so the x-axis is time step, so it is the there's discrete time step. So this is the first time step, then the second time and third time, and so on. So it's the time step. Each one increases by the delta t at that time. The time increases by delta t at that time. And so initially the time steps are small because the solution is changing rapidly. So 1 over delta t is large initially. But later on, when the process is not changing as rapidly, then 1 over delta t is small, meaning delta t is large, and delta t large is allowed because the system is not changing as rapidly. So even with a large delta t, you're still making errors that are less than what you wanted. Now that we know how to estimate error, how do we try to reduce the error? One way to reduce the error in a transient computation is something we have already talked about. This slide is something we have already talked about. So basically here, if the estimated error after some computation compares with these errors that we said we will allow, which is absolute error and relative error that we would allow, if the error compares with that in a way that this condition is satisfied, in other words, the error is less than how much we would allow, then we can either keep that time step or we can try to increase the time step. If this condition is not satisfied, then the time step is reduced and the computations are repeated. This is how we try to reduce error. Now we will see another way to improve discretization of transient calculation. Okay, so recall that when we solved the heat equation, then the time derivative was discretized using finite difference. So it's written as t plus delta t minus t at t over delta t. Okay, this is an approximation of the derivative. Now this calculation, this approximation of derivative is first order accurate, which isn't great. Maybe we can improve. There are ways to improve these calculations. That's what we'll see now. So we will come up with another formula that is for this time derivative, that is second order accurate. So again, we start from the Fourier series, and from that we can write for x minus delta x backward, we can write it this way, and so if I use this one to write in terms of the function being temperature, so t at t minus delta t is equal to t at t minus delta t over factorial 1 del t and del t square over factorial 2, and instead of del square f del x square, I write del square t del t square, and the rest of the terms, just like here we wrote delta x cube and so on, of the order of delta x cube. Here it's delta t cube. Okay, so that's one, and then I do the same. Instead of t minus delta t, I go back 2 steps, t minus 2 delta t. So again, using the same Fourier series, I can write it just like here. Just instead of delta t, I write 2 delta t. Instead of delta t square, I have 4 delta t square. Okay, and that is also accurate of the order of del t cube. So from these two, I can eliminate the this term here. I can eliminate the del square t del t square. How? I multiply this one by 4 times and subtract this one from here. Okay, so I take this one, multiply by 4 times, and then take this one and subtract, and then I get on the right hand side 4t minus t gives me 3t, and 4 delta t minus 4 delta t plus 2 delta t, because we are subtracting, we get minus 2 delta t, this thing, and then the rest of it is of the order of del t cube. Okay, so now we just write del t, the expression for del t, which is all of this other stuff on the right hand side, and since we are dividing it by delta t, then the remainder is of the order of del t squared. And so now we have a formula for del t, the time derivative, written this way, that is second order accurate. So this is better than the one that's written as first order accurate. That is, I'm rewriting this, is approximately t at t plus delta t minus t at t over delta t. This is first order accurate, so this one is generally better. So this is one way we can improve the accuracy. In one software, COMSOL, they give you the choice to choose either the first order or the second order accurate formula for the time derivative that we just talked about. So here you see we have these term called BDF, which is backward difference method. Okay, so a first order backward difference method would be like tt minus t minus delta t over delta t, if we write it that way. And the second order is the one that we just showed in the previous slide. So you can choose the maximum and minimum BDF order. So this is just shows in practice, when you see a command like this, maximum, this is what it's doing. It's either choosing this one or it's choosing the other formula that we just derived. This is how what I'm trying to do is simply not make this kind of an interface as a black box. So you see a term like BDF, we know what it is and what it's trying to do. That's all I'm trying to get at. Of course, we want to reduce error, but it would also be nice if it can be done automatically, if we can automate the reduction of error. That's exactly what we're going to talk about. It's automated discrete reduction of spatial discretization error. Okay, and this is also called the adaptive mesh refinement. This adaptive meshing is basically automated changing of the mesh, and we're going to do the details now. So first you assume a mesh for a computation, and you compute the solution. So here is a mesh that is assumed like we always do, and here is the resulting computation. Okay, now Because we have all the values computed, we know everything, and so we can find the location of the region for the largest changes. So in this case, this was a heat transfer problem. So these are all temperatures. So I know the temperature everywhere. So I know the location where temperature is changing a lot versus where it's changing much less. So here, for example, is lot of change. Okay, and here it's little change. That's why the contour lines are farther apart. So we know where the changes are happening, and we basically want to put more elements in there. We want to have smaller elements in there to resolve those rapid changes, spatially changes that are very rapid. We want to resolve them better. Okay, so in one estimate of how much error we make in one element, we have this kind of expression. I just threw this one just to give you an example of the kind of logic that could be used. So error in each element is bounded by this, meaning it's less than or equal to this value. And what are these? This d squared t dx square, of course, is from the temperature. We can calculate that, and h is my element size. Okay, so in some situation we have this as the estimate of error. So with that estimate of error, because I know d squared t dx squared, because I already did my computation, I know both. Okay, so I basically know where the large errors are. So what I do is, if I want to keep the error more or less constant from this region to this region, then you can see from this expression here, if this is the bound for element size, that, and so I want to then make this part h squared d squared t dx squared a constant. I want to make that a constant because then that will give me a constant error over different elements. And so I can use that as the criteria for remeshing. How do I do that? Because I know all the values of temperature, I can calculate d squared t dx squared. Okay, and I want to keep the product to be a constant. So if the areas where d squared t dx squared is higher, I'm going to make h smaller. Where d squared t dx squared is small, like in these regions where there's little change, I can make h, or the element size, bigger. So I can keep adjusting the element size based on the local solution. So by doing that, basically I can come up with a new mesh. So reduce the mesh size, I mean the element size would be better, element size in those regions. So you come up with a new mesh. So here is an example. So we started from this one, and then based on the calculations, I can find an estimate of error, and wherever there is more error, I put in more elements. So you see, compared to here, here it's more. more elements are put in. Why? Because in those regions, d square t dx square is greater because temperature is changing more rapidly. So I keep doing this at several stages. So based on this, I do one more round, and until the errors are about equal everywhere and they're small. So this process of going from one mesh to another is adaptive mesh refinement, because the mesh is adapting to the solution. But most interesting part of this is this whole process can be automated based on the discussion I just had. So you can program the computer to follow this logic, calculate this quantity, and then decide H based on this relation. So it's like H square is some constant divided by d square t dx square. Because you know the solution, you know this guy, so that will give me an idea of what the element size is going to be. So the whole process is automated, so that's very convenient. And there are several software that actually implement this, and we'll just see one of them. So here is one software that actually implements that mesh refinement process, and it's COMSOL. And all I want to show is, again, to not have it as black box. So this adaptive mesh refinement is built into COMSOL, okay? And in there, you can expect the type of controls that it has. So it has the maximum number of refinements, 3. So it's not like we can do too many of them, and it is often not needed either. And also you give some bounds for the maximum number of elements, so it doesn't become a humongous problem, based on your logic. So, we don't want to get any further details into it. I just wanted to show a real example of that adaptive meshing built into a software. So just to pull everything together, there are 3 ways to reduce error. Okay, we can increase the number of elements. So suppose this is my original mesh. Okay, we can increase the number of elements, so the mesh would change, and this is the most common one, and this is how we can reduce the error of computation. The other choice is using higher order elements. So the original mesh becomes this one. So the mesh here did not change. You notice the mesh itself did not change, but what we did is we added more nodes in here. So this is also called the P refinement, but it's using this higher order element now. So this triangle now, instead of 3 nodes, it has 6 nodes. This is not as common. We don't use it as often. This other one is the most common. Now these two, both of these together, they reduce the spatial error, and then we can also reduce the error due to the time stepping, and that is commonly done by setting error, just like the example I showed in the previous slide. So you set the relative and absolute error in COMSOL, and the program takes a time step, calculates the error, and makes sure the error is less than this in this case in COMSOL and in case of temperature calculation, if the error is not less than this, then it reduces the time step. But this it can do automatically. So those are the three different ways we reduce error in computation. But the important thing is these reductions of error is assumed to propel toward correct solution. It is assumed, it's a very important one. There is no proof. There is nothing that says mathematically that if you do this for every situation, it will reach the true solution. We'll say a little bit more in a later slide. So we have talked about defining the error, estimating the error, and reducing the error. Now we want to talk a little about how we accept the overall model. How do we kind of gauge the error in the overall model, and how do we do this in practice? So first, a very important theoretical statement that we can prove that the solution indeed converges to the correct solution. So the finite element solution converges to the correct solution as mesh is refined. We can prove this mathematically only when the following are true. So interpolation functions have to be chosen carefully. Convergence can be proven only for situations when the elements must be made smaller in such a way that every point of the solution domain can always be within an element, regardless of how small the element may be. And another condition is all previous meshes must be contained in the refined meshes. So under these, and yet another one, the form of interpolation function remains unchanged during the process of mesh refinement. So under these restricted conditions, we can prove that the solution, the correct, the finite element solution indeed converges to the correct solution. But this is only under these restricted conditions. In general, for a given problem, we cannot guarantee this. So what do? We cannot guarantee that as you refine the mesh, it is approaching the correct solution. So what do we do in practice? For practical problems, we do not seem to worry about this, and instead compare the solution with experiment. Did you hear that? Compare the solution with experiment. That is how we take care of practical applications. So again, to remind us, for most real-world applications, the solution we get from the finite element is not really taken seriously unless you have it validated. So you can think of, you really do not have a solution unless you have validated. So the discussion we have been having for error is really in the context of discretization error, because it's only in the context of actual solving of the equations using finite element. Now, we also said that this discretization error in general, for a given problem, there is no mathematical proof, for such arbitrary problem that it will go to zero as the mesh is refined. So we cannot prove that this actually goes to zero for mesh is refined. But then there are other errors in a real-world model. The big one is the reality approximation error, meaning you approximated a real-world physical problem into its governing equation boundary conditions, which are which are just equations. So that is one of the biggest sources of error. And then there are other sources of error, like computer round of error, convergence error, programming error, usage error, and so on. So in practice, how do we estimate those, and what do we do? It's kind of hard. So we end up lumping all of these errors together. We say they're all together and then compare with experiment. That doesn't mean we don't try to reduce each one. So we try to reduce each one, like all the discussion we had in terms of reducing discretization error. Of course, we have to do that. But it is hard to compare individual errors in a real-world problem. So we put all of them together and then compare with experiment. So for validation of most real-world problems, the most powerful way is to compare with experimental data. In fact, it is the only way the results are going to be taken seriously. So after your computation, it has to be compared with experimental data of some kind, either your own or somebody else collected some data for a similar condition. And there are lots of details in that we are not getting into, but it has to be compared with experimental data. Otherwise, the model is not going to be taken seriously. To summarize then, the discretization error in finite element method is the difference between the solution we get using FEM method and the exact solution. Well, it's nice to define error like that. Because we do not know the exact solution, we cannot compute this error exactly. So we estimate the error. And how we estimate error is by comparing the solution we have got with an improved solution, however way we can get it. And one way we talked about was to use a higher order element. So we compare with that and not the exact solution to get an estimate of the error. Once we got an estimate of the error, then we think of ways to reduce error. And there are three ways to reduce error. One is having more elements. And this is by far the most common way to reduce discretization error. And the other choice is to use higher order elements and then smaller time steps for a transient calculation. So those are the ways we reduce the error. And then the acceptance of the final solution, however, is dependent on how it compares with experimental data. So when we compare the solution from a finite element calculation with experimental data, other errors get added, in our solution. Other errors like the physical approximation error that we made to even get to the governing equation boundary condition from a physical problem. All those errors get added. Nevertheless, comparison with experimental data of the calculated results is the only way, is the final proof that the solution that we got is acceptable.